Alright, so if you know the position function of an object, you know how to calculate its velocity. This is the process of differentiating the function. But what about the inverse question? Suppose that you know the velocity of an object. How can you calculate the distance traveled in a certain interval of time? This is the question that we'll study in this video. Okay, so let's start with a very simple case. Suppose that I have an object that is moving at constant velocity. So if I sketch the graph of the velocity function here, I'll get something very simple. Just a horizontal line corresponding to v of t equals to a constant, say capital V. And what I'm interested in is to calculate the distance traveled between two times, say t naught, say 1 hour after the start, and capital T, which could be something like 3 hours after the start. Okay, so how do I calculate the distance traveled? Well, this is very easy. We know the answer. If we're going at constant velocity, then we know that the distance traveled, delta x, will be equal to the constant velocity times the duration of the time interval, delta t. But this formula here is only valid for constant velocity. So how do we actually calculate the distance traveled if the velocity is not constant? Okay, so before we do that, let's just notice one thing. So in this case, where the velocity is constant, what is delta x actually calculating? So capital V here, you can see, is the height of the rectangle, and delta t is the width of the rectangle here on my graph. So delta x here is calculating the area under the velocity function. So here delta x is equal to the area. That's something that is important for the more general case. Okay, but let me now erase this case and let's look at the more complicated case where the velocity is not constant. Alright, so let's consider an arbitrary velocity function, so that would look like something like that. How can I calculate the distance traveled between t naught and capital T? So at t naught here, my object is going at a certain velocity, v of t naught, and at capital T, it's going at a different velocity, v of capital T. To calculate the distance traveled, the idea is to be very, very clever. So I cannot use the formula because the velocity is not constant. But what I can do is split or slice my time interval into very, very short time interval, say 1 minute each. So I'm going to call the time interval, so if this was t1 and t2 and so on, I'm going to take a time interval delta t, which is going to be very short, so 1 minute. Now, over these short intervals, while the velocity is still not constant, but I can approximate it as being constant. Because the time interval is shorter, then the result will be closer to the true distance traveled, right? So I'm basically splitting the distance traveled into short distances traveled for each of these short intervals. And to calculate those, I'm assuming that the velocity is constant over these short time intervals. So over the first interval, for example, I would calculate d1 as being the distance here using the same formula for constant velocity. Over this short time interval, then I would calculate d2 for the second time interval, d3, and so on, all the way to whatever number of time intervals I have. So let me write dn for some n. Now this would give me a good approximation, so I'm using this symbol here because this would be just an approximation of the distance traveled. And in fact, geometrically, what you see was happening here. So we're kind of approximating the area under the curve here by just slicing the area into into rectangles of small width. And it is clear from the picture that the smaller the width of the rectangles, so in other words, the shorter the time interval of my little slices, the better the approximation is. But that still doesn't tell me how I can calculate the distance traveled. This is just an approximation. And this is where things get really crazy. So how do I calculate the distance traveled, which I call d? Well, the idea is totally crazy. The idea is the following. I take the limit where I sent these time intervals here to be extremely small, actually going to zero width. Right? So I know that the smaller the time intervals, the better my approximation. So I'll take the limit where delta t goes to 0. So there's a very, 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 very small time intervals. Now, if I do that, how many rectangles will you need to cover the whole area? Well, if I take the width of each of the rectangle to go to 0, I will basically need an infinite number of rectangles. Right? So this is totally crazy. So I'm kind of slicing the area here into very small, or rectangles of very small width and extremely small. And to actually calculate the area, I'll need an infinite number of such rectangles. But if I do that, then I will get a precise calculation of the area under the curve, or the distance traveled by my object. Okay, so that sounds really crazy, but this is a very important part of calculus. So this process is called integrating, or taking the integral of the function. In fact, it also has a special notation. So for example, in this case, if I calculate the distance d of the function at this distance d, or in other words, the area under the velocity function between t naught and capital T, I would write this as the definite integral between t naught and capital T of the velocity function. Now, this is the notation. It looks a little complicated now, but we will come back to that, and I'll explain exactly why this is a good notation for this process. But this is called integrating. This is called a definite integral. And it turns out that this is really the inverse process of differentiating. Right? Taking the derivative starts with the position function and gives you the velocity function. Integrating starts with the velocity function and calculates the distance traveled, or in other words, the change in position. So it really is the inverse process. In fact, this result, namely that this kind of slicing process is the inverse process of differentiating, is very important. It's called the fundamental theorem of calculus, and we'll come back to that later on. And just as before, here I took the position and velocity as examples, but in fact this process can be done for arbitrary functions. The branch of calculus that studies all of that here is called integral calculus. And it turns out that integrating, or calculating integral functions, is a lot more complicated than differentiating. So what we'll do in this class is that we'll first start by studying derivatives, and later on we'll come back and study integrals, or in the process of integrating functions.